So welcome to Conversations in Science, hosted by the Buffalo Museum of Science. My name is Gabrielle Graham, and I am the Community Partnerships and Adult Programs Manager for the museum. We also have Dr. Jennifer Surtees, Director of the University at Buffalo Genome, Environment, and Microbiome Community of Excellence. Originally, these programs were held at the museum with organic conversations at the end and kind of throughout, but we're very pleased to be able to bring you this virtual version today. We especially thank RP Oak Hill Building Company for their continued support and their presenting sponsorship of Conversations in Science. It's the support of our sponsors, donors, and members that enable us to continue our mission to extend science to our local Western New York community and to serve our community. So now I'll officially introduce our moderator for the panel, Dr. Jennifer Surtees, co-director for the Genome, Environment, and Microbiome Community of Excellence at the University of Buffalo. On a personal note, the UB Gem was one of my first connections that I made coming to the museum, and so it's always wonderful to work with you all, and it feels like having dinner with an old friend. So I appreciate that. And with that, I will turn it over to Jennifer. Oh, wait, sorry, one last housekeeping thing. If you are seeing tons of little squares all down your screen and you would like to see the speaker, on the top right-hand side, you've got a view button. It looks like a little grid and then the word view. Switch that to speaker view and you'll be able to have a highlight on the speaker instead of just on everyone. So with that, Dr. Surtees, I am pleased to have you here, and I'll let you introduce the rest of our panelists.
Thank you so much, Gabrielle. It's I have to return the compliment. It's been a great pleasure over the last several years working and partnering with you in community outreach through GEM, and I think it's been really successful and a lot of fun. And the entire group, the entire panel for tonight is really excited to be here and to talk about vaccines in general and COVID vaccines in particular. And I would just want to reiterate what Gabrielle said, which is that we want this to be conversational. We are going to have a few slides that each of our panelists will go through, but we encourage you to ask questions as we go. As well at the end, because we want this to be more about that conversation and discussion, question and answer than just downloading information. So I'm going to ask each of our panelists to very briefly introduce themselves and why they're excited to be here. And then I'm going to share my screen and we'll start going through the PowerPoint presentation or the slides to sort of illustrate some of our key points. And each of our panelists will speak for a small portion of that. So first, I would like to introduce Dr. Manmeet Bala from the Department of Microbiology and Immunology.
Thank you so much. Good evening, everyone. My name is Manmeet. I'm originally from India. I got my PhD in microbiology from University of Otago, New Zealand, and then I shifted to USA. I'm currently working in UB in microbiology department. My work is focused on pneumococcal infection and pneumonia, which is a community issue globally and also in US. I'm also interested in finding out how can we improve our current pneumococcal vaccines, which will help our elderly community. I'm also trying to find out why our immune system goes weak as we age and how can we improve it as scientists. I'm very excited to be here to share the information. Me and my colleagues will do our best and try to answer any of your questions, any of your concerns for today's topic. Thank you.
Thank you. That's great. And now I'd like to introduce Rasheen Powell, who is in the Department of Pharmacology and Toxicology.
Hello, everyone. My name is Rasheen Powell. I'm a fifth-year PhD candidate at the University of Buffalo, where I study under Dr. Aaron Bhattacharjee. My research is focusing on the underlying mechanisms of inflammation and pain and the discovery of non-opioid analgesics.
Terrific, thank you. And Dr. Tom Melendi, who is in the Department of Microbiology and Immunology at the Jacobs School.
Hi, thank you very much. I attended Cornell and UCLA and then became a faculty member here nearly 30 years ago now. And I've been studying viruses for a long time, including HPV. And last year during the crisis, we started shifting our research to coronavirus and to the COVID-19 virus. And we've been working on finding new ways to screen for antiviral drugs. With the mutations that are occurring in this virus, it's probably going to be a continuing problem, hopefully at a much lower level in society, and we'll need good drugs in order to treat those patients that still end up getting sick. And so that's why I'm excited to tell you about what we've learned about the virus over the past year. Thank you.
Thank you. And finally, Dr. Jill Tirabassi from the Department of Family Medicine in the Jacobs School.
Hi, thank you. Yes, I'm originally from Syracuse. I went to medical school at Upstate. I'm dually boarded in family medicine as well as preventive medicine and public health. And most of my time now is actually being a physician researcher, although I do provide clinical care still. So I'm helping to, help out with dispelling some of the rumors or the misinformation that is circulating right now.
Great, thank you so much. And my research is involved in genome stability in the Department of Biochemistry. And since the COVID crisis hit, we've been actually sequencing, working with the Erie County Public Health Labs and sequencing COVID positive genomes to understand the path of the virus and the variants that are popping up now, which may be part of things that people are interested in. So with that, I am going to share my screen, and we will start sort of the semi-formal part of the presentation, starting with Manmeet.
Awesome.
Yes.
Thank you. Our body has a very powerful army that protects us from different germs or infection. We call this army as our immune system. During this pandemic, we all have been hearing about importance of staying fit, importance of staying healthy, keeping our immune system healthy. And then with the administration of COVID vaccine, all these questions about what will happen to the immune system, how does the vaccine work? So today I'm going to give you a very brief and a simple overview of how our immune system works, what constitutes our immune system, and then my colleagues will build upon this and explain more in terms of current pandemic situation. So every moment our body encounters a lot of bacteria and viruses. This is through the air we breathe, surfaces we touch, food and water we take, and through any interaction we have with our environment. But we do not fall sick, all thanks to our immune system, which gives us immunity. The term immunity itself means the ability to fight infections or germs. So thanks to these immune cells, we have an invisible shield that protects us from any infection. If immune system does not work, then we have a problem which leads to infection or diseases. Our immune system basically falls into two main categories. I'll touch very briefly on these. These are cells belonging to the innate immunity and the cells belonging to the adaptive immunity. The innate immunity is something that we are born with. These are the cells of our immunity that kills virus or bacteria in a very non-specific way. When I say a non-specific way, it means it does not distinguish between a particular virus, a particular bacteria. Its purpose is to just kill. So these cells of innate immunity, they either eat these germs or they release certain chemicals from their cells that are really toxic to these invaders, bacteria or viruses, and kill them. Now we have different type of innate immune cells in our body. This is the list of these cells. These cells, different cells, they might have common or specific proteins that act as toxins against bacteria or viruses. These cells act very, very quickly and they roam in our body 24/7. And they are just ready to fight within hours of infection. And they are the main reason we do not fall sick on daily basis. But somehow when our innate immune cells are not able to take care of the infection or the intruder, they call for help from the second branch of our cells, which is adaptive immunity. In adaptive immunity, we have B cells and then we have T cells. T cells are further characterized into T helper cells and the T cytotoxic cells. Now, as the name adaptive immunity suggests, this immune response adapts to every kind of infection in a very specific way. It is very specific, and our body produces B and T cells, which are specific to every kind of virus or bacteria, and helps our body to get rid of these germs. These B and T cells, they identify the germs based upon different proteins present on the surface of bacteria or virus, which we call as antigens. Antigens means something that doesn't belong to our body, they are foreign. T cytotoxic cells, as the name suggests, these are toxic to those cells which are infected. So they release certain proteins and just lyse or kill those infected cells. B cells, on the other hand, produce Y-shaped antibodies. We all must be hearing these days about the antibodies since the COVID vaccinations have started. These antibodies are very important to get rid of infection. These bind to the surface of bacteria or virus and prevent these to binding to our own cells. And if a virus is not able to bind our cell, they cannot infect. So that is important to know. Also, once these antibodies bind to bacteria or virus, it becomes very easy for our innate immune cells to come and just eat those. Then the T helper cells, they just help both these T cytotoxic cells and the B cells to do their function as their name suggests. So one of the important aspects of adaptive immunity is its capacity to keep record. It retains memory as we all do. If a virus enters our body for the first time, B and T cells, they take some time to figure out that it does not belong to our body. Now, why this is important? This is important as you do not want our cells to get activated to something or against something which could also be a part of our own body. It can damage our cells also. So after making sure that the thing which has entered our body is a stranger or an intruder, these B and T cells, they get activated and kill the intruder. So it takes some time initially. But then it also memorizes that intruder, and next time when it enters our body, these cells act very, very fast. They already know that this one does not belong to our body and needs to be taken care of quickly. So this is also shown on the graph on the right side, where you can see the first exposure to bacteria or a virus produces a slow and a mild response, but the subsequent exposure to the same virus or bacteria produces a fast and strong immune response. Now, this whole forms the principle on the basis of vaccination. My colleague Rasheen will now explain about the basis of vaccination and how it benefits us or our body in general.
So we can pause here briefly if anybody has any questions, please. This is a good time to ask about antibodies or adaptive immunity if you have any questions at this point. If not, we can move on to Rasheen. So I think, one of the things we wanted to emphasize was just the way that our body responds to the vaccines naturally, and then how that we take advantage of that in terms of when we use vaccines and design vaccines. We do have one question. If I donate antibodies, and we've heard some people doing this with convalescent antibodies, if I donate antibodies, do I run out of them? Manmeet?
Yeah, that's a good question. No, we do not run out of antibodies. Our body is well equipped to keep on producing antibodies on regular basis. So you can donate antibodies and your body won't run out. So.
Great. Yeah, that's a question that I've heard a lot. So thank you for sharing that one. Okay, Rasheen, would you like to pick up from here?
Yes. So, what I'll be touching on is how do vaccines actually benefit your immune system? So, my background is less so in immunology and virology and more so in neuroscience and pharmacology. So, I went about this in a way that I would like to be taught how do vaccines benefit your immune system because I'm kind of well, not kind of, I'm much less versed in this, but I still have an interest. So, one of the things that we talk about in neuroscience is learning a task, something that you do repetitively where you gain some type of aptitude for. So, in the real world, these are things like learning an instrument, or let's say you want to practice or you want to run a marathon. You would run a set distance and gradually increase it over time such that you become proficient at it. So, as a child, you may study hard for a test, or as an adult, you may practice to land a job. All of this is just under the idea that you practice, 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 or repetition is necessary for you to reach a certain level of aptitude for that any given task. Well, the same is true for the immune system. Vaccines is honestly just a form of practice for your immune system. It is a way for the body to be exposed to some form of pathogen or virus that you may normally not be exposed to, such that you can develop some form of innate immunity, some form of intrinsic immunity, so that if you do come across that disease or that virus or bacteria out in the real world or in the wild, you will be readily equipped to fight it off naturally. So normally, this controlled exposure may be facilitated through some form of weakened or inert form of the pathogen, or maybe even a protein that is specifically expressed by that pathogen so that the body can identify it, recognize it, and hopefully amass an immune response. So later down the line, if you come across it again, you're already prepped and ready to go. So I drew a little cartoon at the bottom where, in the case of vaccination, you have some immune cell coming across this vaccine, it has no idea what this is, the first time it's ever seen it, but it'll amount to a small or moderate immune response. However, if you were to come across it again, your body's already prepared and it's seen this before. But what has actually come across is the vaccine or whatever was used to elicit that first immune response. But this time, your body is well prepared to fight off that infection. And then you get a much more robust response. And sometimes you may not even realize that, hey, you've come across or you've been exposed to this virus. You may just go on about your day with a runny nose for a day and then keep it moving. So why is this important? Right now, we all of us are all of us understand that we are in a COVID crisis, and we must understand the basis of this disease. And one of the most important things to understand about COVID is its life cycle, such that we can move forward into the vaccination stage. So the life cycle of SARS-CoV-2 or the coronavirus or COVID-19 starts with primary infection and the cell finding its necessary receptor. So SARS-CoV-2 binds to the ACE2 receptor that is expressed by certain cells. So it can only bind to, or it only binds to this receptor and it infects cells that express this receptor on its outside or on its cell membrane. After it binds, you have this event where it gets internalized into the inside of the cell. So now it's actually in the cell itself. And once it's in the cell, you have this uncoding event that occurs. Once this uncoding occurs, you have a release of the virus's genomic information into the inside of the cell. And this is now the RNA genome. This is the instructions necessary to create copies of the coronavirus. These instructions include viral proteins and also viral RNA, which will then be packaged in a network or in a process, a highly complex process that utilizes a bunch of different proteins that are expressed or that are coded by that RNA genome that eventually result in the formation of these vesicles packed with many more copies of that original viroid particle. And then those vesicles are then trafficked to the membrane, where they are released and allows for subsequent or further infection of other ACE2 expressing cells. Now, the reason why we're going through this and the reason why we want to highlight the SARS-CoV-2 life cycle is because that interface between the virus itself and the ACE2 receptor has been identified as a very promising article or very promising interface for vaccine development. And the theory when this all happened was that, hey, maybe if we could stop this from happening, we could prevent infection and we could help to increase the outlook of those who may come in contact or decrease the amount of spread in a population. And that's where the vaccines come in. So that's the end of my section. If anyone has any questions, please do not be afraid to ask.
So we have a question from the chat. Why do some individuals take ill when they receive a flu vaccine? So Dr. Tirabassi, would you like to answer that question?
Yeah, I would be happy to. So it's true that many people have that response to a vaccination that makes them feel ill. And it's basically your body's immune response reacting to the vaccine. And so you can have things like fever and chills and those symptoms that we've been hearing about, sore arm, but you're not truly falling ill with the actual disease. You're feeling the effects of your immune system working. And so that's a common thing that we're seeing and we hear about, and it's unfortunate, but the way to think about it is it means that your immune system is doing its job. It's reacting and it's going to protect you.
Thank you. Yeah, I think, we went through how the immune system works, and there's a lot that goes on, and then a lot of physiological responses to these viruses. Let's see, we've got something else in the chat. How did they know which protein on the coronavirus surface was the one to make the vaccine against? Dr. Melendi.
How did you know I was ready for that? Thanks for your question, Chris. While COVID-19, the SARS-CoV-2 virus, is new, scientists have been studying coronaviruses for a number of years. And it was known that the spike protein on other coronaviruses, due to various studies, it was found out that that was the protein that was involved in binding to whichever receptors that they evolved to utilize to get taken up by other cells. And it's true in other viruses as well. Often there's other viruses, like I'll show you one in a little bit. Adenoviruses also have a protein out at the end, which is the first contact protein. And the idea behind it is if you can stop, and we'll get to that in a few minutes, if you can stop that initial contact protein from contacting the cell, you can prevent the virus getting into the cell. So it was an obvious place to start looking. And it worked.
And it did work. It is working. And I just want to highlight the fact that this highlights the importance of doing basic research so that we have a fundamental understanding of how things like viruses work and how this is one example where having the basic knowledge and basic understanding of how the virus gets into the cell, for instance, has really benefited us. And there's a lot of research that's been going on for decades that's been extremely useful, whether it's genome surveillance and doing sequencing and the bioinformatics behind that, so we can trace the variants and where they are, to using the ACE2 inhibitor, to testing antivirals and that sort of thing. So it's all as I said, it just emphasizes the importance of basic science, I think, and understanding mechanism. We have another question in the chat. What if you don't get sick after a flu vaccine? Does that mean you were previously exposed to the virus? Or other questions, does it mean it's not working?
And Dr. Melendi answered that in the chat as well. Everyone's immune system is a little different. You can be immune even if you don't get a strong response to the vaccine. And I just wanted to chime in here because I thought that Rasheen's comments about practice and exercise really kind of hit home for my understanding. Thinking about the first time that I rode a bike all the way up a steep hill and how difficult that was. I also come from a place that has a lot of steep hills, so apologize, Buffalo. The first time I did it, it was extremely hard. When I did it again, it was a little bit easier. And so the more you exercise your immune system and are exposed to a variety of things, the less kind of burn you'll feel afterwards when you're exposed to a new pathogen. And so thinking about your immune system as another muscle that you need to flex, you kind of need to continue to keep it maintained and keep yourself well and hydrated, or you will experience that kind of post-exercise burnout in the same sort of way with immune reactions. So thank you. That was a good metaphor. Thank you very much.
Okay, I think Dr. Melendi, it's time for your segment. Would you like to share your screen? In the meantime, we do actually have another question. After infection, where do memory B cells reside, and how does the body protect them? Do they divide and replicate in response to repeated exposure to upregulate antibody production? Dr. Bala, would you like to address that question?
I was speaking on a muted one. Thank you. Yeah, that's a good question. The memory B cells, they keep on dividing. Once our body produces a functional B cells which secretes antibody and the memory B cells, these memory B cells, they move out of the blood, and they have been found to localize either in bone marrow or they go to spleen, where they divide on regular basis. And second thing, what we have found in research, or what people have found in research, is that they have extended lifetime. So they don't need to divide as often as the regular B cell that is actively producing antibodies. So they are taken care of in specific niche, you would say, where they maintain their population for a long time, if that helps.
Okay, let's learn about vaccines and COVID vaccines in particular.
Okay, I realized I'd forgotten to unmute myself at first. Do you have one slide in front of you now? Can you see my slide?
Yes, we can.
Great.
Yes, yes.
And we see your cursor as well. It looked like you had a red highlight that was floating around. We can see that.
Excellent. Thanks very much. So yes, all vaccines work in the same general way. They're presenting a target for the immune system. They do this education, or this exercise, if you will, so that our immune system learns the pathogen and then can act against it. Different targets can be used. The simplest version was to actually use inactivated virus. Vaccines against the SARS-CoV-2 virus are educating or training to recognize the virus or parts of it to produce protective antibodies, right? So what we're trying to do is generate these antibodies. This is my depiction of an antibody, and each one of the ends of an antibody can bind to a virus particle. Sometimes vaccines utilize an inactivated virus, and this was the traditional way of doing it. It's been done a lot in the past. And this inactivated virus, this way the virus has been hurt or weakened so that it won't cause disease. And you can inject an inactivated virus and you can generate an immune response. And again, these were the older traditional ways of doing it. But nowadays we often want an even safer situation. So we look for very specific targets. And I'll tell you a little bit more about, again, this spike protein that has been determined to be the target, and how the vaccines that we're now utilizing and will be utilizing in the future were devised for this. You've seen this. Dr. Powell did a nice job of describing the viral life cycle, uncoding and how you produce virus. And this spike protein is actually the target for the vaccine. And a couple of the mechanisms that the vaccine is using in terms of antibodies, at least, is that these antibodies are able to block the spike protein from binding to the ACE receptor, so it prevents the virus from getting in the cell, but it can also cause the virus particles to cluster into larger groups with antibodies around it, and our body knows to dispose of those things. Although we haven't mentioned it, we've been focusing on antibodies, there is also the T-cell immunity pathway that Dr. Bala talked about. And that is, these vaccines are also teaching our cytotoxic T cells to attack cells of ours that are actually starting to produce virus. So we're not only getting the free-flowing virus, but we're also going and attacking infected cells to suppress the infection. So here are some of the different approaches that are being utilized to display the spike protein to our immune system so our immune systems can learn about it. The two vaccines that are out there now and are being injected into people across the country and across the world are the Pfizer and Moderna vaccines. These require 2 doses, and they're utilizing a new technology, which, although this technology has been under investigation for about 20 years and was actually on the verge of starting to be utilized actually for cancer treatment, is we were able to utilize this platform very rapidly. And these are actually why they're the first vaccines out there. And we are probably going to see many more of these mRNA vaccines in the future. What they do is they include a small mRNA molecule that's packaged in a lipid bilayer. And when these are injected, they actually go into our cells. I should point out that this mRNA encodes for the coronavirus spike protein that we've been talking about. And when this goes into our cells, in this case, when we're injected, for example, in our arm, these generally go into our muscle cells that are there. They don't spread probably throughout our whole body. They probably stay fairly localized, and that's why there's localized pain. And it programs these cells to express the viral spike protein. So you now have this on the surface of your cells, and this is then seen by the immune system as something foreign, and it can produce both B cell and T cell immunity. I've been depicting this as an antibody, but remember, in particular, by being on the surface here, it's very good at producing T cell immunity as well. So it stimulates both branches of our immune system. 2 new vaccines that are actually in the pipeline and are in late stage 3 trial. In fact, they could be approved for use any day or any week now, are the AstraZeneca, is that vaccine, which is a UK vaccine, as well as the Johnson & Johnson vaccine. And this utilizes a different virus, an adenovirus. You notice this has a very different look about it. This cartoon, it's actually a cartoonized, colorized version of an electron micrograph, honestly. And this shows you, as I told you, that other viruses also have spike-like proteins. In this case, these are referred to as fibers and knobs. And an adenovirus is another type of cold virus. And lots of us are infected by adenoviruses every year. And in this case, both of these companies have taken an adenovirus, they've taken slightly different adenoviruses, and have modified the virus so that they've included information for the spike protein so that it sticks out on these knobs. And so here you have this modified adenovirus with spike proteins, coronavirus spike proteins stuck out here. Now, of course, we don't want to inject people with cold virus, so we inactivate this virus, which is an old-fashioned, again, sort of an old-fashioned approach. But adenoviruses produce a very potent immune response. So when these are injected, you get, again, a very potent antibody response, and it recognizes that spike protein. Also, Novavax is about ready to come out with a recombinant protein vaccine. This is a common pathway for generating vaccines around the world. And a number of the international vaccines, I believe the China vaccine, I think the one in Russia as well, is essentially utilizing a recombinant protein approach. This also requires 2 doses. And what we do essentially in this case is in laboratories and facilities, we overexpress the viral spike protein. Then this is included into a oh, I can't think of the name of, the name of this thing right now. A nanoparticle, that's what it is. These are incorporated into a nanoparticle. And what these essentially are is a slow release thing. So if you take a cold medicine, for example, their time release, this is the same idea, but at a small molecular level. And then over the course of the next few days, it slowly releases this antigen, and this goes out into your immune system. And it also produces an immune response, which recognizes the spike protein and makes antibodies. This approach might be more antibody specific rather than a combined B cell, T cell response, but all of them seem to be producing fairly robust responses to coronavirus, and so that we have an antibody response to it. One thing that I would like to point out, since the mRNA vaccine is a new technology, unlike the others, even though it's still been studied for 20 years, is when this is injected and this lipid bilayer fuses with the cell, the mRNA goes into the cell, very similar to what happens when the virus infects. And this mRNA doesn't produce a whole virus, but it just translates one protein, the spike protein, which comes out, is produced in vesicles, transported to the surface, and then your muscle cells produce this the spike protein on the surface to be recognized. The main thing I wanted to point out is there's been some questions of whether or not this RNA could get into your genome, and affect your DNA, your hereditary information. What you can see here is that this RNA, all of this is occurring in the cytoplasm. It doesn't go into the nucleus. It doesn't have any way of going into our DNA chromosomes. In fact, our cells in our body don't have a way of turning that RNA into DNA to insert into it. So there's no danger that this vaccine is going to infect your genetic information. So therefore, there's no reason why it would cause cancer or change your body's phenotype that way. So I think that's all I had there. Hopefully I can answer any other questions that you might have on this. Has anyone been looking at the chat? I'm just seeing it now. Where did memory B cells reside? Did we answer that question? I forgot.
We've answered that one. Yep.
We answered that
Yeah,
question.
so Tom, I got it. So has there been any study into utilization of the currently approved vaccines in a therapeutic sense, that is to help people who are sick already with moderate or severe disease?
I don't think there has been, and the reason being is that I know there are a few people that are considered long haulers that may retain the virus for a long time. But for most people, the viral infection occurs over a short time, and the damage in many cases is often an effect of an overactive immune system. And that's why a number of the treatments for people with advanced COVID is actually something to suppress the immune system. So a vaccine to enhance the immune system once you're infected is kind of trying to close the barn door after the horse has already left, if you will. It's unclear if long haulers would benefit from that. But again, long haulers are usually suffering from issues of an overactive immune response. So it's probably not a good thing to do, a useful thing to do.
And what is the status and timeline for developing a COVID vaccine for pediatric patients? Dr. Tirabassi, would you like to take that one?
Yeah. Right now, I know that Moderna and Pfizer are both doing the older pediatric population, age 12 and up. My understanding is they're still in some recruitment phase. I think the timeline I've seen is maybe by later this year, end of this year, for that age. For the younger ones, from what I've seen so far, it could be a lot longer, even next year, before there's a vaccine that's safe and tested for them.
Which makes it important for those of us who can get vaccinated to get vaccinated. What is the origin of the adenoviruses?
So the two vaccines that are out there are utilizing two different adenoviruses. Adenoviruses are often called a cold virus, but honestly, we respond to them, it's more like a mild flu. It doesn't cause the secondary problems of the flu, meaning the pneumonia that kills people. But it's a normal circulating infection that occurs every year. One of the two vaccines is using a human adenovirus, and another one is using a monkey adenovirus, simply because I think the justification behind doing that is we're less likely to have an overactive immune response to it because we wouldn't have been infected with it before. But adenoviruses are something that affect us frequently.
Maybe Rasheen or Manmeet can address this one. Why is the current RNA vaccine effective against the new virus variants that are showing up? So many of you may have heard of the three main ones, more easily transmissible variants, one from the UK, one from South Africa, and one from Brazil. And early tests suggest that the vaccines are remaining effective against them. So I'll let you answer the question after setting that up for you.
So as Dr. Melendi just explained that these mRNA vaccines, they lead to production of spike protein that is identified by our immune system and produce antibodies to block. Luckily, so far, with all the variations that have been found in this virus, the spike protein has not changed. So whatever antibodies that our body is producing in response to this vaccination is still able to identify, bind, and block the spike proteins even in these variants. So it's still effective. So the overall spike morphology of the virus has not changed.
There's probably also has to do with the T cell response as well that Dr. Melendi was mentioning. So it's more than just the antibody affinity that is involved in that response. How rapidly can we produce the various types of vaccines? Is culturing the virus required for any of them?
That's actually a really good question, Vance. For example, the yearly influenza virus, we've got this, the infrastructure is in place. We know how to culture new viruses. It still takes something like 9 or 10 months to get a flu vaccine. So that's why often they have to predict what the next strain is going to be, and they don't always hit it correctly. This is a little bit different. If you've noticed, the first two vaccines that are out were actually the mRNA vaccines, even though they had not already had FDA approval. Because of the way these vaccines are made, they can be developed more rapidly than other types of vaccines. And that's why, interestingly enough, this new platform is the first one that is actually getting into people's arms in a large scale. I don't know how fast it is, but let us simply say that the mRNA vaccine technology is such that if it is now being proven effective, we will be able to do rollouts in a much faster time frame than we've ever been able to before. In fact, it would not surprise me if over the next 10 or 20 years that mRNA type vaccines may very well become one of our most common types of vaccine platforms.
Great, thank you. I think it's, yeah, the mRNA technology is really exciting. I would like to move on to our last segment. Dr. Tirabassi is going to tell us a little bit about herd immunity and how vaccination can help us get to herd immunity. We have one question, another question about the pediatric vaccines. Would a pediatric vaccine be developed as differently structured mRNA molecule, or is the delay due to the time it takes to do further studies, safety studies, and efficacy studies in children? So,
my understanding is they need to adjust the dose based on for the age of the pediatric patient. I don't believe that they would be changing much of the vaccine itself. It's mostly a safety dosing issue.
Thank you.
Okay, are my slides good?
Perfect.
Okay, so the last part is talking about herd immunity, and I'm sure many people have heard of this in the news. And basically, herd immunity is indirect protection of community members. So basically, if enough people are immune to the virus, it'll reduce the chance that others will get infected. And there's two primary ways of becoming immune, if you will. It's getting COVID and through the illness itself, or getting vaccinated. And obviously, we know getting vaccinated is a safer route as of right now. There's not a specific number. People are just guessing and projecting, how much of the population needs to be vaccinated to achieve herd immunity. The ranges I've seen are from 70 to 90% will need to be fully, vaccinated to achieve herd immunity. So we're not quite there yet. The last numbers that I saw as of yesterday were that New York State is at 1% fully vaccinated. So we got a lot of people to go. And in COVID, herd immunity, we're talking about protecting our young kids, especially infants, those who probably will not get a vaccine anytime soon, protecting members of our community that are immunocompromised, say cancer patients, transplant patients, people who probably will not have a robust immune response even if they get the vaccine, as well as those who are vaccinated, but the vaccine didn't work. As we all know, we have a really, really great vaccines right now. We're talking 94 to 95% effective, but that does leave, at least 5% of people that get the vaccine that will not be protected. And then obviously there's others who won't get the vaccine, whether they have a history of anaphylaxis to one of the ingredients in the vaccine or other reasons. There will be people who aren't going to get vaccinated. So hopefully we can keep that number very, very small. We're going to go through quickly in the next 3 slides some graphics to try to better understand this idea. And basically there's going to be 3 different color of people. There's the blue people that are healthy, not immunized. There are red people who've gotten sick because they've not been immunized. And then there's the yellow people that'll be immunized, healthy people. So first, this is basically a year ago when we have an unvaccinated population. If we have 2 people who are sick and contagious, as we all kind of saw, many people around them can become infected. And so it can spread, as we go from the left side to the right side, it can spread kind of like wildfire through all of our, through the population. Thankfully we started to understand the virus, and we knew to lock down and do masks and social distancing, but that can happen. The next scenario now is where we have some of these yellow people, these people who are immunized and healthy that are in the population, but still most people are blue. They're not immunized. And so those 2 sick red people still can pretty much infect the majority, or at least a good portion of the population. And, most of the people who are immunized will be healthy, but as I don't know if you could see up in the top corner there, an immunized person could also become sick if they were one of that small percentage that did not have a response. So the hope is to get to this last slide where we have a large portion, the herd, if you will, a large portion of our community that is vaccinated. So now we have those 2 sick red people again, but they really don't have as much access to those non-immunized blue people, whether they be the young children, whether they be the immunocompromised, or people who couldn't get the vaccine because of allergies. The hope is that we can protect those people, because most of us who've gotten vaccinated aren't going to get sick or are less likely to spread the illness, and so we can prevent the spread of the virus and the disease process. I just want to also thank Dr. Melendi for making these slides. So I think I saw a question pop up. Ooh, I'll stop my share.
Yeah, we actually have a couple of questions. Sorry.
Okay.
We actually have a couple of questions.
Good.
So one is whether or not you are still potentially a carrier once you've been vaccinated.
Yeah, that's a really good question. The hope is that with enough people getting vaccinated, we're not going to allow the disease to spread to those who are. But we don't know the answer to this one for sure. We think that there's a lot less chance that if you do get infected and spread it, that you have a much lower viral load, so a less chance of spreading. But it is possible from what I've seen so far. We don't quite have all the answers yet.
Right, that's when it's better to be cautious and keep distancing and masking, and while we find out. Another question, does the 70 to 90% required for herd immunity include or leave out people who have natural immunity because they were already infected by SARS-CoV-2?
Another good question. They're saying vaccinated population because we don't know how robust people's immune responses really are to the actual disease process itself. We think it could be a less robust immune response, and we don't think it lasts as long as the vaccine will in terms of, you know, how many months out. The current thought process that right now from the CDC is that if you get infected, you potentially are immune for about 3 months. We know with at least the Moderna vaccine that the vaccine response is lasting longer than that, but on both ends, we don't quite have an exact answer to that. But like I said, in general, the herd response is based on the vaccine because it does last longer than the other.
Right. And even if it isn't a long lasting, like years lasting, it could be an annual vaccine that similar to the flu. We just don't know those things right now.
Right.
I have a question actually that came in ahead of time. So the medical community mentioned that individuals with seasonal allergies could have an adverse reaction to the vaccine. Could you comment on this and what is done for those who may have serious reactions?
So I think it's important with that question to point out seasonal allergies and serious allergies. Those with seasonal allergies are completely recommended to get this vaccine. I myself suffer from seasonal allergies, and I have got the vaccine. It's really the people who have a history of anaphylaxis, whether it be food or medicine. That history is much scarier, and those people need to be monitored for longer after their vaccine. The only true contraindication, meaning the only true reason to not get this vaccine, is if you know that you've had anaphylaxis to something that's in one of the ingredients that's actually in the vaccine. And you can, if you find out, you know, which vaccine you're potentially available to get, you can look at the list of ingredients and make sure. But I would always talk to your allergist or your doctor about it as well.
Tom,
Dr. Melendi.
go ahead.
No, absolutely agree entirely with that. I would like to point out that we have to look at relative risk. And I think out of 4 million people, for example, treated with the Moderna vaccine, there were 10 cases of anaphylaxis. And if you think about the number of people and all of those were treated successfully, they all survived. And if you think about the number of people who are likely to die from the absence of vaccine, for 4 million people, you're talking about roughly, what would that be? 40 to 80,000 deaths. So we have to think about, you know, relative risks and keep those numbers in mind.
And if I could add to that, not only the risk of death, but also the risk of the prolonged effects of COVID following infection or the resolution of the disease. So in my case, or as the data was coming out, there were cases of college athletes who were being infected with COVID-19 and then presenting with myocarditis at the age of like 21. they have inflamed hearts. So you really have to consider not only the physiological, the pulmonary effects, but also the vascular effects. And in my case, or more interest to me, the neurological effects that are come along with it as well. So it's not just whether you live or die, it's also if you survive, or there's a high chance of survival, but what are the potential fallouts afterwards, 5, 10, 15 years from then?
Yeah, that's a really important point that not everybody thinks about when we focus so much on the mortality. We don't think about those effects. There was another question that was submitted ahead of time, and that was about the side effects that are associated with with the vaccine and how sometimes those side effects can be severe for some people. We talked about different people having different immune systems and therefore having different reactions. So, Dr. Tirabassi, can you talk a little bit more about what those side effects, what people should expect, and sort of how to mitigate them, and if there's a particular issue with older patients?
Yeah, sure. So, every time you get the vaccine, you should be getting the handout, which is going to list, basically any side effect possible. The most common ones that we're seeing right now are sore arm. We see fever, headaches, and muscle aches and pains and chills kind of as the next group. And then others, can happen as well. Typically, because right now we have the 2-dose vaccines, the side effects tend to be worse after the second one, which if we think about that curve picture, we get a bigger immune response after the second one. So that makes sense. It can, cause fatigue in some people. And so, if there's someone who's might be frail or, a family member that you could be a little worried about and their reaction, I think, it makes sense to make sure that you're monitoring them and that everyone, knows of their situation. In general, it's actually younger people, those with a more robust immune system, that are having worse side effects. But we just can't predict how people are going to respond to the vaccine, so it really could happen to anyone.
Is there any chance that there will be long-term side effects of the vaccine, ones that won't turn up until many years after receiving the vaccine? Anyone?
I'll answer that. I know that there are things that we just don't know. And because this is a newer emerging disease and the treatments are new, we don't know that yet. And part of the kind of beauty and tragedy of science is that there's lots of things that we don't know. And sometimes the best thing that we can do is continue to collect data. And so we can make assumptions based on what we've seen in the past, but predictions don't always hold true. And so honestly, that's just something that we don't know yet, but I'll defer to the people with medical degrees as well.
Tom?
I agree with Gabrielle completely, but I'll point out again, we also don't know the long-term effects of COVID infection, and we know the numbers are much higher, even for the intermediate term effects. We've got a lot to learn there as well. And personally, I'm pretty sure that the long-term effects of a COVID infection are far, far worse and far more likely than the long-term effects of a potential vaccine long-term effect that we cannot foresee.
I think that is an excellent point to bring us to the end of our program. As always, I really appreciate the partnership with our folks at GEM and the Jacobs School of Medicine and Biomedical Sciences. I have dropped a link to a quick survey in the chat. If you have time, it just takes 2 minutes and it's so valuable. And this is a free program. And so we ask you for just a little bit of information about what you thought about it. And this helps us going forward in developing new programs and new presentations. Also, you can stay up to date with the Conversations in Science series by following us on our websites. Those links are now in the chat as well. And you can view past Conversations in Science on our YouTube channel. Also, if you are feeling well and healthy and have a mask that covers your nose and mouth, you are welcome to visit us in person at the Buffalo Museum of Science. We are open on Fridays, Saturdays, and Sundays. You can see our COVID protocols on our website at sciencebuff.org. And then coming up on February 13th, we will be opening a new temporary exhibit which is called Medieval to Metal, the Art and Evolution of the Guitar. And so if you like thinking about evolving processes in vaccines or in the instruments that we make to pass the time while we are quarantining, come out if you're feeling well and healthy and have a mask that covers your nose and face, and check out Guitar Medieval to Metal. But thank you so much to all of our speakers tonight. We really appreciate the time that you've taken to prepare this information for the public. And I know that I'm feeling much more informed than I was previously. And it's always good to have you out and to talk with the people. We really appreciate it.
Thank you so much, Gabrielle. We had a lot of fun putting this together and really thinking through this, and we really appreciate the opportunity to share this information.